Hi folks, today we're looking at differentiating logarithmic functions, and the good news is that they're also super easy, just like exponentials were. So there are proofs in the video description down below. You can check out why these work the way they do, but I'll let you know the derivative of ln x, which is a log with a base of e, is 1 over x. So what does that look like if you differentiated something that is not just x, something that has an inner part? So ln of x squared. Well, what we'll do when we differentiate is we'll use our rule. So if it had been ln x, it would turn into 1 over x. If it's ln of x squared, it'll turn into 1 over x squared. And then the chain rule will apply. So we'd have to multiply by the derivative of the inner part. Put that all together, and we'd have dy by dx is 2x over x squared, or just 2 over x. Now let's make some rules out of that. If we tried to use the chain rule here, ln of x turns into 1 over x. Ln of f of x is going to be 1 over f of x times the derivative of f of x, because that's the chain rule. Now, because it looks like a fraction multiplied by something else, we could also simplify this into just f prime over f. So let's do that. And that's how I remember this, or really almost how I remember it. Let's make this look kind of nice anyways. So the derivative turns into the original function that you were taking the ln of on the bottom and its derivative on the top. And I remember it like this. Original on the bottom, derivative on the top. Original on the bottom, derivative on the top. And I just have that little ditty going in my head. So if I took this function right here and used that little trick, I could go straight to original on the bottom, its derivative goes on the top, and differentiating it is super easy that way. I want to show you one other thing that you could do here. You could also use log laws. So from 621b, we know there's this power law of logarithms where you can pull a power down front. You can also split logs apart. If you have ln of a times b, that's the same of ln of a plus ln of b. And these rules work for any base. It's just we're going to be working with a base of e most frequently. And ln of a over b turns into ln a minus ln b. So I can also go ahead and simplify this function before I differentiate. I could have taken this 2 and put it down front. Now this is still y equals. I just used this first log law, and I pulled the 2 down front, and now I can differentiate. That might even be easier. 2 is going to stay, because it's a coefficient. Ln x turns into 1 over x. And we get this answer of 2 over x, no matter which way that we do it. Whether we think of it as chain rule, whether we sing it, or whether we try and use log laws on the way. When things get rough, it's going to be important to use log laws to make them easier. We'll do a couple of these where we do it a few different ways, but after that, I'll just always default to the easiest way, and likely I'll sing my derivatives. I've got ln of 2 over x here. I can use some log laws. I can use this third log law, and I can just split them up. Call it ln 2 minus ln x. That's not differentiating, just using these properties. Then when I do differentiate, ln 2 is a constant, so it turns into 0. And this one, ln x, turns into 1 over x. So my derivative becomes 0 minus 1 over x, or just negative 1 over x. Now you might say, okay, but I wanted to sing this one. I wanted to put the original on the bottom and the derivative on the top. All right, we can do that. We can go original on the bottom. So when I say original, I mean this 2 over x. Its derivative goes on the top. Finding the derivative of 2 over x is actually a bit of a pain. So we might take an extra minute to work that through. I think I'd have to think about this as ln of 2x to the minus 1. This is an x to the minus 1 here because it's an x on bottom. So if I want to sing my way through this derivative, I'll go original on the bottom, derivative on the top. The derivative of 2x to the minus 1 is going to be negative 1 comes down, so that's negative 2. And this power goes down by 1. Okay, let's check it out. The negative 2 and the 2 are going to divide out and just become negative 1. This is really an x that should have lived up top, this one right here. This is an x squared that should have lived down below. And I get the same answer, but I think it was a lot easier to use the log laws first. And there might be other methods that you can come up with here that are subtly different from these, but should all get you the same result. Here's another one that has a natural logarithm in it. I look at my log laws, there's none of them that I can use here because this whole thing isn't raised to a power. There's no multiplication or division that I can use to split them up inside here. All I can do is sing. So to differentiate this, and the song has the chain rule built in. It's original on the bottom, derivative on the top, derivative of 3x squared is 6x, derivative of 2x is 2. Factor it if you like. And we're done. In fact, we were done here as well. So 2 different ways of writing the same answer. And that's it. In this next one, we've got a product. We've got sine x times the ln of 3x. So I'll be clear here. My u is sine x. We know that its derivative is cos x. My v is ln of 3x. I could mess around with some log laws here, but I can also just sing. This one's pretty straightforward. So v prime's going to be original on the bottom, that 3x on the bottom. Its derivative on the top, so derivative of 3x is 3, or 1 over x. Now when I differentiate, pretty straightforward. U prime, v, plus u, which is sine x, v prime, which is 1 over x. We can put those together in a bunch of ways, but I think I'd like just cos x dot ln 3x. If you don't have brackets here, it's implied that it's still, that whole 3x term is having a log happen to it. And then this would be sine x, and I could call it sine x over x if I wanted to. Let's have plus here in between them. That's one way to present the answer. Or you could leave it like this. Okay, we're in the swing of it now. We've got our song. So I can just go original on the bottom, derivative on the top. But if this is my original, look at it. It is a quotient with some chain business happening in it. It is going to be very, very difficult for us to find that derivative on the top. So instead what we should do, even though we could just use the song right away, we should use our log laws, and we should use them before differentiating. Before differentiating. So let's see what that looks like. It's still going to say y equals, because I'm not differentiating yet. But I see this third log law here, this division. So let's write this out. Sine x to the 4 minus ln of 5x squared minus 3. It's like this was my a, and this was my b. And now we could differentiate. But what would be better is to use all the log laws we possibly can before differentiating. Because here, if the original is 3x plus sine x all to the 4, finding its derivative is going to be a pain because it's going to have its own chain. So let's pull this 4 down, and that is a log law. That is not a differentiation pulling the 4 down. So 4 ln of 3x plus sine x minus the ln of 5x squared minus 3. Now we're ready to differentiate. dy by dx. 4 is a coefficient, it's going to stay. And original on the bottom, so that's 3x plus sine x. Derivative on the top, derivative of 3x is 3. Derivative of sine x is cos x. Minus, here's a separate one. It's another logarithm to differentiate. And it's super easy. Original on the bottom, derivative on the top. Derivative of 5x squared would be 10x. Okay, so putting it all together, this is 4 by 3 plus cos x all over 3x plus sine x minus 10x and there's a correct expression for our derivative. If you had done it with the song right away at this first step, number one, we'd probably still be doing it all day. And number two, it will probably look a little bit different because it'll be over a common denominator, but it won't be worth the extra time and effort it takes. So use log laws before you differentiate to make the question easier, and then sing your way through the differentiation. One question that might arise next is, what do you do with other bases? And you might or might not remember from 621b the change of base rule. It says that you can work in any base that you want. So if you have log base a of b, it's the same as ln b over ln a. Or you could have written it as log base 10 of b over log base 10 of a, or whatever base you want. So we can change bases easily, which means that secretly we can always be working in a base of e, which turns out to be our most convenient base. If I have y equals log base 5 of x, using this change of base rule, I could rewrite that as ln x over ln 5, okay, just using these properties, which are true. And I could write that again as 1 over ln 5, just split apart this whole thing, times ln x. And after we do this question, we'll have a rule that we can use, and we won't have to go through these shenanigans every time. But when I differentiate this, it's actually pretty easy. It's going to give me 1 over ln 5, that stays as a coefficient, times 1 over x, where the derivative, if you have a base of 5, turns into 1 over ln 5 and an x on the bottom. You have an x on the bottom, just like you always did. And then you have to pay a price for using a weird base. You have to put a ln 5 there, just like we did for exponentials. It's just now it shows up on the bottom. So if this had been log base 7 of x, you'd have a ln 7 here. If it had been log base pi of x, you'd have a ln pi here. If you have log base anything, log base a of x, then you'll have a ln a on the bottom. And you'll still have this 1 over x. So let's make a rule about that. Let's say log base a of x differentiates to 1 over ln a, and an x on the bottom as well. Let's do it for the function. If we had log base a of f of x, everything's going to work the same way. We'll still have original on the bottom, derivative on the top, but we will pay the price for using a weird base. So we'll need a ln a here. So the rules are really the same no matter what base you're using. It's just if you have a base other than e, or something other than a natural logarithm, you've got that extra tax that you have to pay of ln a. Let's try one that uses that. So this one has a lot going on. It has a strange base, it has a product, it has a square root, there's some chain stuff happening in there as well as a product. We can go ahead and use this rule over here, which is original on the bottom, derivative on the top, and pay the tax for a weird base. But what would be smarter would be to use our log laws. So I've written them here in terms of natural logs, but they work for any base log. So let us split this apart. This is log base 7 of x squared plus log base 7 of the square root of sine x. I'm going to call that sine x to the half because it's more easy to deal with in a differentiation context. And now we could sing our way through the rest of the derivative. Or we could use some more log laws, and that would be easier. So for all these powers, I can pull them down front from that first log law. This turns into 2 log base 7 of x plus 1/2 log base 7 of sine x. Now I'm ready to differentiate easily. dy by dx. 2 stays, and it's going to be original on the bottom and its derivative on the top. Or since it's just x, I can just use the little rule here. But make sure I pay the tax for having a weird base of 7. So it's 2 times 1 over ln 7 times x, all on the bottom, plus 1/2. All right, again, I'm going to sing my way through this derivative. So original on the bottom, derivative on the top, and pay the tax for that weird base. So there's my ln 7. I can put this together and make it a little bit prettier, not that much. Let's see, this is a 2 times 1, so 2 over ln 7 times x. Sometimes you'll see them written as x ln 7. That's great too. I just like to make the distinction that this is the tax that you're paying. It's not really part of the chain rule. What do we have here? We have a 1 over 2 ln x, or sorry, 1 over 2 ln 7. And I would call this whole thing cotangent x. So times cotangent x. Or if you want to, you could put that cotangent x on the top of this fraction. There's a correct expression. Let me just write it out a little cleaner. There we go. So use those log laws first. It'll make things easier. One nitpicky thing that we've glossed over is that the domain of logarithmic functions is restricted, typically. And that's because you can't take the log of 0 or of a negative number. So if I had this function here, ln of 3x plus 7, and I tried to put the number negative 3 in for x, I'd have ln of, well, negative 9 plus 7. I'd have ln of negative 2. You can't do that. And that means this graph doesn't exist at x equals negative 3. You can find its domain pretty easily by saying, listen, whatever's in here has got to be positive in order for us to be able to talk about the function. And then you can solve that inequality and get x is greater than negative 7/3. That's the domain of this function. Everywhere it exists is at x value is bigger than negative 7/3. Now, if we think about its derivative, we can sing it, right? Original on the bottom, derivative on the top. It looks like in this function you can put negative 3 in and you'd end up with some value that's okay. But that would be silly to do so. That would mean that you could talk about the slope of this function where it doesn't exist. Bizarre. So any restrictions that exist in the domain on the original also need to carry through into the derivative. Even if it doesn't look that way algebraically, even if it looks like it's okay to put in, say, big negative numbers here, this function ceases to have meaning where the original one doesn't exist, because f prime means the slope of f. The big idea in this section has been use log laws when you can, and use them before differentiating. If you differentiate a logarithm, the easiest way is to just sing it. Original on the bottom, derivative on the top. And if you use a base other than e, so if you use, say, log base 2, then you have to pay a tax. You have to put a ln of whatever that is on the bottom. The chain rule is built into the song, so don't double chain rule it. As long as you're singing it, then you should be okay. There are some practice questions down in the video description, so take a look at those. And let me know if you have questions.